Hello, it's Richard Hammack's Calculus 1. We are in part 5 of the course on integration. Most recently, in lecture 38, we introduced the process of antidifferentiation, also known as integration. It's the reverse process of differentiation. We're now going to build on that in 3 lectures, 39a, 39b, and 39c. The first topic is what are known as initial value problems. But first, before we talk about that, a quick recap of lecture 38. Remember that the indefinite integral, sometimes just known as the integral of a function f of x, is denoted as the integral of f of x dx, and it stands for a set of functions big F of x plus c, which is all of the functions big F of x plus c whose derivative is little f of x. You can think about this as it's all the antiderivatives of f of x. That's what this notation stands for. And the process of finding the integral of f of x dx, remember, is called integration, and it's the reverse process of differentiation. If you have a function big F of x plus c and you differentiate it to get a function little f of x, then if you integrate little f of x, that's going to take you right back to big F of x plus c. So these two processes are the reverse of each other, integration and differentiation. And we had a whole list of integration formulas. For every differentiation formula we had for a function, we could write it in reverse and get an integration formula. So for example, the integral of 1 over x dx is ln of x plus c, meaning that ln of x plus c is all the antiderivatives of 1 over x, and you can confirm that by differentiating ln of x plus c, and you get 1 over x. And similar remarks hold for all of these formulas. There are 3 more for the inverse trig functions run in reverse, or their derivative rules run in reverse. And we also had a constant multiple rule and a sum difference rule. In all of these antiderivative formulas, there's a plus c. And as we've seen, that could be any real number. Beginning today, we'll be thinking about problems in which you can actually find the c. There may be enough information to say what it is in certain problems. That's our goal for today. But before reaching our goal, I have to tell you something significant about this number c. We've been quietly using a consequence of the mean value theorem that we talked about back in lecture 35. It states that if f prime of x equals g prime of x for all x in an interval I, then g of x equals f of x plus a constant c on I. You can rephrase this in terms of antiderivatives. If f prime equals g prime, then the two functions f and g have the same derivative, so they are antiderivatives of the same function. And this statement becomes, if f and g are antiderivatives of the same function on I, then g of x equals f of x plus c on I. So we've been using this fact in writing our antiderivative rules. When we write the integral of little f of x dx equals big F of x plus c, we mean that all of the antiderivatives of little f of x have the form of some function big F of x plus a constant. But according to the sentence above, this is only true, it's only guaranteed to be true, provided f is defined on one single interval I, and not multiple intervals. And I'll show you an example of what I mean by this. Think about the function f of x equals ln of x, or more properly, ln of the absolute value of x. It has a graph that looks like this. This is defined on two intervals, the positive real numbers and the negative real numbers. ln of x is not defined at x equals 0. And that breaks the number line up into two pieces. I'm going to write another function, g of x, whose derivative is the same as f of x. On this first interval, for the positive numbers, let's add a constant to f of x. So we move this graph up by c units, whatever c is. And we're making a function g of x in blue. But what I'm going to do is on the other side, I'm going to add a different constant. So I move this up a different y value. And we get this blue function, y equals g of x. Now notice here that for any x, f of x and g of x have the same slope. So g of x and f of x have the same derivative. G prime of x equals f prime of x for all x. And f prime of x, f is ln of x, so f prime of x is 1 over x. So the derivatives of both g and f are 1 over x. So f and g are both antiderivatives of 1 over x. But notice here that the function g of x, it's not f of x plus c. It's not this black function f of x moved up c units. There's no c that does the job. So you can see here that not all antiderivatives of f of x have the form of f of x plus c. This g of x doesn't. And the problem is here that we have two intervals that the function is defined on. And as noted up here, for this integral to be equal to f of x plus c, things have to be defined on one single interval. So when we write something like the integral of 1 over x dx equals ln of the absolute value of x plus c, we are assuming that the functions are defined on one single interval. So for instance, in this case, maybe we're talking about just the positive real numbers or just the negative real numbers, but one single interval. Here's the takeaway. Technically speaking, all of our integration formulas are stated for the integral of f of x dx, where f is defined on one single interval. For the most part, you'll never have to worry about this. E to the x, b to the x, sine x, cosine x, x to the power of n, where n is positive, they're defined for all real numbers, so there's no issue. But for other functions like 1 over x, which is defined on two intervals, or maybe secant squared x, which is defined on infinitely many different intervals, these formulas are stated for any one single interval in their domains. For the most part, like I said, you never have to worry about this. If I'd never mentioned it, you'd probably do all of the problems in this course just fine. But do keep this in the back of your mind. Let's get back to our main goal for today. We're all about finding c. Let's look at an example of this. Suppose f of x is a function whose derivative is f prime of x equals 1 over x plus 3x. So maybe you don't know f of x, but you do know its derivative. It's this. And let's say you also just happen to know that f of 1 equals 5. From these two pieces of information, the derivative and f of 1 equals 5, we want to find the function f of x. Let's think about how we'd go about doing that. Well, our f of x that we're looking for, it's an antiderivative of its derivative, which is 1 over x plus 3x. So we can start to find f of x by writing it as the integral of 1 over x plus 3x dx. That's the set of all antiderivatives of this derivative. And we should be able to do that. Let's change this x to x to the 1, so we're ready to use the power rule for integration. And the integral of 1 over x is ln of x Here we are with the power rule to integrate 3x to the power of minus 1 right here. And then we have a plus c at the end. And simplifying that, we get ln of x plus 3/2 x squared plus c. So that's our function f of x. ln of x plus 3/2 x squared plus c. Now notice we don't quite have our exact function f yet because we don't know what c is. This c could be any real number. In order to get this explicit function that meets these two properties and has f of 1 equals 5, we need to find c. Think about how we could do that. There's one piece of information we haven't used yet. It's f of 1 equals 5. And let's write that down. And down here we have an expression for f of x. Sure, it's got a c in it. We don't know c. But basically we have f of x except for knowing what that c is. And up here it says that if you plug in 1, you get 5. So if you plug in 1 to get ln of 1 plus 3/2 1 squared plus c, that has to equal 5. Let's write that down. So here's 1 plugged into our f of x, and it equals 5. And this simplifies. Ln of 1 is 0, and we get 0 plus 3/2 plus c equals 5. And notice there's an equation here, and c is the only unknown, and we can solve for it. We get c equals 5 minus 3/2. Let's get a common denominator. And finally, c equals 7/2. So that's the value c has to have in this function, and that gives us our answer completely. F of x equals ln of the absolute value of x plus 3/2 x squared plus 7/2. You can check that it's a solution to our problem. Take its derivative. You will get 1 over x plus 3x. And if you plug in 1 to it, f of 1 would be ln of 1 plus 3/2 1 squared plus 7/2. Work that out, you get 5. So we've got a solution to our problem. This equation, f of 1 equals 5, that we used here, where we know a function value, that's sometimes called an initial value. So from that initial value, we were able to find all function values f of x, which is this. And that's why these are called initial value problems. So get some practice on ones like this in the exercises, and we'll move on. In our final topic of the day, we're going to revisit motion on a line and update it relative to what we've learned today. Remember the situation of an object moving on a straight line whose position at time t is s of t. In that setup, we know that the velocity of the object at time t, which we denote as v of t, is s prime of t. And also the acceleration at time t, which we denote as a of t, that's v prime of t. So here, by taking derivatives, we go from position to velocity to acceleration. It would make sense then that by taking antiderivatives, you could go from acceleration to velocity back up to position. In fact, because the derivative of velocity is acceleration, that means velocity is an antiderivative of acceleration. So this v of t equals the integral of a of t dt. And likewise, because the derivative of position equals velocity, our position function is an antiderivative of velocity. So we've updated the formulas for s, v, and a. In addition to v and a, velocity and acceleration being derivatives of position and velocity respectively, now position and velocity are these antiderivatives given here. Let's take an example of this. Imagine a ball is tossed straight up, like in this picture. Straight up, and it has a position function of s of t. It has a constant acceleration of minus 32 feet per second, which is the acceleration due to the pull of gravity. And let's say that at time t equals 0, the initial velocity is 20 feet per second, and also that ball is 5 feet high. So right here at time t equals 0, it's 5 feet high. You might imagine that you're holding that ball 5 feet above the ground, and you toss it straight up at time t equals 0 with the initial velocity of 20 feet per second. It starts going up, and it eventually starts to slow down, get slower and slower, and maybe it eventually starts coming back down. Well, definitely it does. So from all of this information, the problem here is to find that position function s of t. What is it? Give its algebraic expression. Let's look at what we know. In this problem, we know the acceleration. It's minus 32. No information about velocity is given except at time t equals 0, its velocity is 20. All we have is what the acceleration is. This is a of t equals minus 32. And we want to get back up to s of t. So the strategy here could be, we know a of t, take the antiderivative of acceleration and get velocity. And once we have velocity, take its antiderivative to get position. Sort of work our way up by taking antiderivatives. Let's give that a try. So the velocity at time t is the integral of a of t dt. And our a of t is minus 32, so we have the integral of minus 32 dt. So what's an antiderivative of minus 32? Well, that would be minus 32t plus c. Just a simple antiderivative problem. So we have a formula for velocity. V of t equals minus 32t plus c. But we don't know what c is. But remember, we have an initial condition. At time t equals 0, the velocity is 20 feet per second. So that means when you plug in 0 for velocity, you get 20 feet per second. And this v of 0 would be equal to minus 32 times 0 plus c. And that gives us an equation that says c plus 0 equals 20. So c is equal to 20. And we can update our velocity function. Now we know what c is. V of t equals minus 32t plus 20. That's our velocity function. But what this problem is asking for is not velocity, but position, s of t. Well, up here we know that the position is an antiderivative of velocity. It's an integral of velocity. So to find position, s of t, we just take the integral of v of t. That's the integral of minus 32t plus 20 dt, which is minus 16t squared plus 20t plus c, just a standard integration problem there. So we found our s of t almost. S of t is minus 16t squared plus 20t plus a constant that we don't yet know. So to solve our problem and to find s of t, we just need to find c. Well, what could we do here? There's one piece of information that we haven't used. At time t equals 0, the position is 5 feet. So that tells us that if we plug in 0 to s, we're going to get 5. But also, on the other hand, if you plug in 0 for s from this formula, you get minus 16 times 0 squared plus 20 times 0 plus c. Look at that equation. You now have c equals 5. So having found this c in the second integration problem, we've got our position. Just plug in c equals 5. So s of t is minus 16t squared plus 20t plus 5. And that's it. We found the position function. I hope this example illustrates how these new ideas of integration and initial value problems have applications to physics. And really, this is just the tip of the iceberg for that. That's it for today. In lecture 39A, we've looked at initial value problems. That's all about finding C from extra information, from initial values. Next up, lecture 39B is going to be on what are called differentials. We'll make sense of these entities dx and dy that we've seen a lot of in calculus, but we've always been a little bit vague about what they are. We're going to make that precise. And doing so is important because it leads to a topic of differential equations, which is very important in applications. And it's all about finding y, or f of x, from derivatives. We'll build on what we did today in lecture 39C, using this new idea of differentials. That's the plan. I'll see you next time, and goodbye.